there were three problems. One of the problems came from the Dirac equation. The Dirac equation describes electrons moving in atoms. And these electrons have very high speeds. The Dirac equation is a very successful explanation where quantum mechanics and the special relativity theory are combined. So basically you're looking at very small things in very small spaces, moving at ridiculously high speeds, and the Dirac equation really describes that. Only that the mathematical solution also gives a negative energy, which is really insane. This is, I mean, energy has to be zero or positive, but not negative. So that's really weird. You can ignore it, of course, but out comes this solution, so you have to do something with it. The second problem was that if you look at radioactive decay, beta decay is it called, where the electrons come out of the core, then it was understood that this neutron somehow changed into a proton and outshot an electron. Now if that happens, the total energy should be the same. Now the proton stays behind at roughly, well, zero velocity. So you would expect that the energy, the kinetic energy that the electron has, would have been the same every time. Because it's the same, basically it's a neutron, well, changing into a proton, shooting off an electron. Why would the energy be different every time? They didn't understand that. So that was another problem. And the third problem was, how do you stick these particles together? How do a proton and a neutron stay together in the atomic nucleus? I mean, a neutron is neutral. And even worse, how do you stick two protons together? They repel, right? You should have some other thing that keeps them together. So these were three problems that need to be solved. The solution came, for the first one, came with, from Paul Dirac. The equation that describes the energy of particles is up here. So the energy squared is this, P is the impulse, the momentum, basically the energy in moving particles. And this, of course, is Einstein's energy. If you have a particle with zero momentum, then only this part is left, so E equals mc squared. That's basically the rest energy, as we say, the energy in the mass. If the mass is zero, then E equals pc. But if you have a particle that has mass and velocity, then the energy squared is this. And then, of course, you know from math, the energy then is plus or minus the root, right? So, and that's the minus root. So what he said is, well, perhaps these are not electrons with negative energy. They are electrons with positive energy, but the opposite charge. That would also work. So he made this prediction a couple of years later, where he said, well, these anti-electrons really exist, and when an electron and an anti-electron meet, they annihilate completely. This was in 1931, and already a year later, Carl Anderson did experiments on cosmic rays, basically very fast particles from outer space, and they had a bubble chamber. Basically, a bubble chamber has this mist of liquid particles, basically liquid drops, and if a particle hits that, you can see this track in the mist, like planes make in the sky, sort of condensation track. Now there's a lead plate here, and that's meant to break these particles. So if you see this track, you don't know from which direction the particle is coming, right? But if the particles are decelerated by this lead plate, then basically, if you deflect them with a magnetic field, a slower particle will have a smaller curve than the faster particles. So we now know this has happened, and from the deflection to the left, we can tell that it's a positively charged particle, and also by looking at the way this is curved, we can tell you something about the mass-charge ratio again. So we found that these are the particles that have the same mass as electrons, but positively charged. In this article, the positive electron basically is the proof of the first proof of antimatter. So antimatter has always been a very, well, a spooky thing, but antimatter is all around us. These particles, they come out of a banana, basically, for instance. So they are all around us. We never notice them, of course, but because most matter is normal matter, not antimatter, but it has always been there. And a couple of years ago, I was at CERN, and they have this building there that looks like this, and that's of course a great name. So if you have this, then you put this on the building because it looks fantastic. Of of course, there was a book written about that, a very successful film. That was completely ridiculous, but anyway, this is not. This is the antimatter factory at CERN in Geneva. And they do research on antimatter. They even created anti-hydrogen. So with an anti-proton, with an anti-neutron, with an anti-electron. So this is anti-hydrogen, and they do research on that, and they even look if these anti-particles have a different interaction with gravity. They're not falling upwards, that's not the case, but you should look if they are falling down differently. So far, that is not the case, which is, good to hear, but also a bit sad, because you really want something special happening, and then perhaps new physics is on the way. So.